Let's start section 5.3. Riemann sum and the finite integrals. So here is the first definition of what's the meaning of Riemann sum. Let f be defined on a closed interval. And keeping in your mind, always we're gonna use a closed interval because we need to find the area. That's mean from this point to this point. And let delta be a partitions of AB. Remember when we divide the whole area to rectangles, that means this is going to be the width. Divide the interval AB to how many rectangles or how many the delta, which is we have the partition the interval given by here's the first number of the interval and here is the last one. So we're going to divide to x1, x0, x1, x2, x3. That's why x0 is less than x1, x1 less than x2, and keep going until xn, which is equal be the last number of the interval. Where delta xi, these points here, is the width of the subinterval I. Here's the subinterval, the first subinterval. Here's the second subinterval. Here's the third one. It looks like you're doing, this is A, and here's B. So I'm gonna say here is x0, because x0 is the first number. Here is x1, x2, x3, x4, and keep going x5 until the last one, x6. That's what you're doing. So delta xi, here is the first width. Here is the second one, the third one. This is the width of the subinterval xi minus 1 and xi. That's mean here is the subinterval. So this is the width. Here is a width. Here is a width because here is x4. So here is x4 and x5. If ci is any point in the subinterval, so here is, we're going to check that with the next graph. Ci is the points here, C1. Here is C2, C3, C4. That's mean the point between the subintervals. C5. If Ci is any point in the subinterval, then the sum of FCI, which is because you're gonna plug in CI in your function to get, this is the Y. FCI with the width. That's mean it looks like rectangle. So because you're gonna take this is F to the CI, C1. That's mean you're gonna graph a rectangle here. You're gonna graph another rectangle here, another rectangle here. We're gonna check that with the graph. The sum with the width, this is a rectangle, is called Riemann sum. So this is the Riemann sum. We already took this one last class. So here is the Riemann sum. But now we're gonna add, because remember, if we divide the area to 5 integrals, we're gonna get an error. To minimize the error, we have to maximize the number of rectangles. So every time you maximize the number of rectangles, you're gonna minimize the error. That's mean you're gonna, when delta x going to infinity, that's mean maximize the width to infinity number of rectangles. In this case, the error is going to be going to the 0. So that's mean we're going to go to the exact area. So here's just the width of the partitions is denoted by, remember that we did this one, it's b minus a over n, where n is the number of the partitions. We're going to check that, but now we have to add the limit. So when I add the limit, that's me. When the width going to the infinity, we're going to minimize the error until to the 0. The defined integral is the Riemann sum, but we have to add the limit. So the same thing, we know this is the Riemann sum. Let f be defined on the closed interval AB, and the limit of the Riemann sum with the partition. So here is the Riemann sum. This is the Riemann sum. but I'm gonna add the limit because I need to maximize the number of the rectangles. That's mean minimize the width. So every time when I minimize the width, I'm gonna maximize the number of rectangles. That's mean the limit with the width going to the 0. If the limit of the Riemann sum exists, then f is said to be integrable on the interval AB, and the limit is denoted by. So now, instead of doing this one, we're gonna say, okay, we're gonna go back to the integral. I'm gonna say, okay, the integral from the region from A to the B, this is the lowest number because it's a limit integral. It's not integral in general, it's a limit integral on certain area between A and B. That means these are numbers from x equals 0 to x equals 5. But that's our goal. We have to find the interval AB. I need to find the area from which point to which point. And the area, the rectangle is going to be with the x or with the y. So that's the difference. F of x dx. So now, instead of doing the limit for the Riemann sum, I'm going to say, okay, I'm going to do the integral. Here's my boundary for the interval, my function dx or dy, f of y dy. It depends about, you're going to do the integrals with the x coordinate or you're going to do the integrals with the y. It depends how you're going to find the area. The limit is called defined integral. That's been integral with the limits from A to B, and A is the lower, and of course the B is going to be the upper or the last number of the interval. Write down these. So here's the next part. That's what we're going to use when the define integrals as an area of region. So every time when they ask you find the area, that is going to be your goal. You have to set up the integral because they're not going to give you the integral, but they're going to give you the limit, or sometimes they're going to give you the graph, and you have to set up the integral by finding the lower limit, the upper limit, and f of x dx or f of y dy. So this, if you want to find the area between, you're going to use this one. If you want to find the area between a function, like for example, this is the function and the x coordinate. It's going to be like this. What about if you want to find the area between the f function, the graph, like one of these examples with the y? So it's going to be f of y dy. So if you look to these two examples, that's what we're going to do. And the first part when we start explaining, so here's A and here's B. And you check, here is the intervals. The first, the width, delta x, x1, x2, x3, x4. So that's, we're gonna divide, here is the sub-interval, the first one. And here is the second sub-interval, and keep going. That's mean, what we're gonna do, as we said, we're gonna choose a point between the first sub-interval, a point between the second, the third, the fourth, and the fifth. Now, here's going to be f to the C1, f to the C2, f to the C3, and here's f to the C4, keep going. F to the C5. That's mean, you see, we're gonna get integrals, rectangles. So this is the Riemann sum, the summation of all these rectangles, which is the f to the c with the width. The sum of these is going to be Riemann integrals with the width is going to be b minus 8 divided by m. So that's the whole thing, but we're not going to do the Riemann sum, but we're going to use the integral. Because every time, which is the limit of Riemann sum, is going to be the integral. So this one is going to be like an easier way to find the area. See what it says here? As you increase the number of rectangles, you decrease the width, of course, because the width is going to be smaller of each rectangle. Then you will decrease the error, and that's our goal. We need to decrease the error, so we're going to approach to the exact area. So the area is going to be more accurate. That means if the rectangles go into the infinity number of rectangles, that means like infinite number of rectangles, you're gonna decrease the area, the width is going to be to 0. That means the here is going to be the Riemann sum. That means every time when the width going to the 0, the limit of the width going to the 0 for the Riemann sum, you're gonna get the exact area. So they're telling you set up the defined integral that yields the area of the region. So that's our goal. Of course, they're going to give you the function. So this is our function. The graph of the function, I need it from this point to this point, because that's what they're going to ask you, find the area for this region. That's mean we need to set up the defined integral. So it's an integral. My function with respect to the x. That means the function is going to be 4x minus x squared dx. Then that means if it's for the dx, our rectangles is going to be with respect to the x. That means our rectangles is going to be like this. That's it out. Our rectangles is going to be like this. I'm just going to graph more than one rectangle. I just need to know my rectangles start, I'm telling you, with the x coordinate. So start from this point and the end to this point, because my rectangle is going to be like this. So the rectangle start is going to work like this. Here's the first rectangle, the second one, the third one, the fourth one, and keep going like this. Start from 1 and end to the 4. So my limit for the integral from 1 to the 4. That's the whole thing. We're not going to find the area. I just need to set up the defined integral. So here is the defined integral. If you want to find the area, you just have to integrate this one, and then that's what we're going to do in the next section.
Wait, how did you find the 1 and the 4 again?
The one from the point, because you see, here's 1, 2, 3, 4. So I need to find the area. My graph started from this point to this point. It's not started from the 0. So here's 1, 2, 3, 4, 5, and keep going. So started from 1 to 4. My rectangle is going to be with x coordinate. It started from 1 to 4. So from 1 to 4. You got it?
Yes, sir. Thank you.
Can you see this line?
Oh, yeah, I can see the line.
That's the important part. Just to set up the integral. We're going to do the integrals next section. The same thing for the next example. For the next example, you have to be careful. You see, your function with the y, f to the y equal y squared plus 1. And they're telling you y is greater than 0. That's mean only on this side, the positive side. So my integral is going to be for the function, which is y squared plus 1 dy. Was my function with the y. And be careful. That means the rectangles is going to be for the y. Your rectangle is going to be like this. Your rectangle is going to be worked like this with respect to the y coordinate. Start from y equals 0 to y equal 2. So it's for x, the rectangle is going to be like this. From x equal 1 to x equal 4. For the y, the rectangle is going to be like this. From y here 0, because I need to find this area. From y equals 0 to y equal 2. So the limit is going to be from 0 to 2. That's it. So that you have to be careful. If you want to choose to find the area like this rectangle, it's going to be for the y, or you're going to choose for the x. Okay. So now check this example. They're telling you evaluate. If they're telling you if the integral from 2 to 4 x cubed dx equals 60. So this is given. The integral from 2 to the 4 x dx equals 6. The integral from 2 to 4 dx equals 2. Be careful. Check the integrals for each one the same boundary from 2 to 4, from 2 to 4, okay? Now we need to find the integral from 2 to 4, 1/4 x cubed minus 2x minus 9. The first thing, I'm just going to use the rule of integrals. I'm going to say, okay, it's the integral for the first one, the integral for the second one, the integral for the third one. That means this one is going to be the integral from 2 to 4, 4 x cubed dx minus the integral from 2 to 4, 2x dx, and minus the integral from 2 to 4, 9 dx. The next step, I can take 1/4 out the integral, the same thing for the 2, and the same thing for the 9. So it's going to be 1/4 the integral from 2 to 4 x cubed dx minus 2 the integral from 2 to 4 x dx and minus 9 the integral from 2 to 4 just dx. Now if you look, here's the integral and here's the second one and here's the third one. We already know how much it's going to be. 1/4 the integral from 2 to 4 x cubed dx equals 60. So 1/4 times 60 minus, here is 2. The integral from 2 to 4 x dx equals 6. So this is times 6 minus, here's 9. The integral for the dx equal 2. So this is times 2. 60 divided by 4, 15. 15 minus 12, 3. Minus 12, 3, minus 18. How much is going to be? Minus 12, minus. Something. How much is going to be? 21? Negative 21? 21. Minus 12 plus minus 9. Yeah, I think I have a different number. Oh yeah, that's why I got different because I put different sign. So how much going to be? Negative 15, because here it's a plus, I have it. So now it's negative 15, which it doesn't matter. 15, and here's negative 12, negative is going to be 30. So it's going to be, yeah, 15 minus 30, it's going to be negative 15.
Why is negative?
Which one?
Negative 15. Oh, that's the final answer.
Yeah.
Okay.
Because here's 15
Yes.
minus 12 minus 18. 12 with the 18 is 30, negative 30. That's mean 15 minus 30. But I have different sign when I solve it. That's why I said, what? Like I remember I got 21. So it doesn't matter. Also evaluate. So we have the integral from 2 to 8 x cubed, and we have the integral from 2 to 8 x dx will vary. Let's go from 2 to 8 dx equals 0. Be careful. The same boundary from 2 to 8. if there's one difference, you can't find this integral. You can't evaluate by using this information. We have to use the method we're gonna do for section 5.4. So now we're gonna, this one is going to be equal the integral from 2 to 8. The first term, which is x cubed dx, minus the integral from 2 to 8, 11x dx, and plus the integral from 2 to 8, 3 dx. Then the same thing, we're gonna take the 2 out, 11 and the 3. So it's going to be integral from 2 to 8 to the integral from 2 to 8 x cubed dx minus 11 integral from 2 to 8 x dx plus the integral from 2 to 8 plus the 3 integral from 2 to 8 dx. Again, we have the integral here, and we have the integral here, and we have the integral here. That means it's going to be 2 times the x cubed is 1020 minus 11. The x is 30 plus 3. Dx is 6. It will be 1,700. 1,700. Here's for the last example. We need to sketch the graph. First of all, do I have the function?
It's 2x.
So, because we already know the integral for f of x dx. So I know the function here is f of x. That means f of x equal 2x plus 3. Now again, I need to sketch this graph. So I'm going to choose 2 points. Let's say if I choose x equals 0, that means f to the 0 is going to be 2 times 0 plus 3, which is equal 3. That means when x equals 0, 1, 2, 3. When x equals 0, there is my point. Now I need to choose another point, but check the limits. Why I choose x equals 0? Because my boundary from x equals 0 to 2. I need to find this region from 0 to 2. That means the next part, the next point is going to be x equal 2. That means f to the 2 is going to be equal 2 times 2 plus 3. So 4 plus 3 is going to be 7. So when x equals, here's 1, here's 2. It's going to be 1, 2, 3, 4, 5, 6, 7. Let's do it here. Here's the area. So here's a 3, and here's 7. So now this is my graph. You see, I have to learn how to graph it. That I took the function, here's the boundary, which is x equals 0 and x equals 2. I'm gonna graph, here's my boundary, here's my function. Now I can graph it. The next part, we're not gonna use the defined integral to find how much it's going to be, because the second part, here's the graph. I need to use geometric formula to evaluate the integral. Because if you look at this one, it's a trapezoid. It's a trapezoid. Here is the first length, the smallest length, and here is the highest length. That means the area is going to be equal. And here is the base, which is 2. The base is 2. is going to be, who remember the formula for trapezoid? The smallest height and the highest height. So it's going to be 3 plus 7. What else? You remember that? It's by 2, but we have to put down the base here. The base, it's A equal base divided by 2 and height 1, height 2. The base is 2 divided by 2. And the first height is a 3 plus 7. Cancel these, so the area is going to be 10. That's it. So we didn't use this integral. So next section, if you use this integral, your result is going to be also 10. But now this is geometric figure, okay? So we can use the trapezoid to find the integral. But if we have like a curve here, instead of this line, if we have a curve, we can't use the trapezoid because it's a curve. Even if it's small, it's not a line. So we can't use the geometric formula, but in this case we can. So it's a trapezoid. We're going to use the formula A equals B over A, the first height plus the second height, divided by 2, and the result is going to be 10.